Okay, thanks for coming to the last lecture, everyone. So today, I'm gonna still talk about Hamiltonian simulation a bit, but I'll spend maybe 1/4 of the time talking about it and then switch to slightly different topics. So it'll be about some extensions of the methods that we discussed. And also, we've been also talking about algorithms that are very that we know will work eventually, but it will probably happen in the far future. And of course, there are very active activities in using near-term quantum computers. So I'll talk a little bit about that as well, but that'll be for the second half. Okay, so we learned last time that qubitization is a very flexible framework for developing quantum algorithms, in particular for quantum Hamiltonian simulation. And and many of these recent advances were based on the select plus prepare subroutine, which, and as I said, there has been many recent work which tried to utilize these special structures in the Hamiltonian.
Excuse me, can you remind us what were the special structures that
Yeah, so I guess I didn't discuss about this too much, but so ultimately, qubitization, you can break it down into select and prepare. And so it's usually the prepare part that's quite costly. So if you have an arbitrary, so it's interesting to consider two different limits. So let's say we have to, let's say the coefficients of the Hamiltonian are all different. So we have alpha p. So this is our Hamiltonian. And let's say alpha p are all different. Then you have to prepare, actually, I think this will be better. And if alpha i's are all different, then prepare requires preparation of log 2 n qubit state. And the cost is typically like order n. But if alpha I are all the same, then you just need to prepare a uniform superposition state. And that's very easy because what you need to do is that if you have a, say, n qubit system, then what you need to do is that you begin with the tensor product of all zero state, then you apply a h to the tensor of n. So well, let's remember little n is log 2 n, big N. So here the cost is like order log n. So clearly, this is a somewhat simplistic example, but what this shows is that if there's some structure in the coefficients, if most of them are the same, then we can often reduce this cost significantly. And that's what I mean by special structure.
Okay, thank you.
Okay, so I think this is a good time to sort of do an overview of what we have learned. So the focus was Hamiltonian simulation. And we talked about, I guess this is the reverse order. So in the beginning, we talked about Trotterization, and then LCU, and then qubitization. And we follow the historical development. And in some sense, as you move from this 3 to 2 to 1, in some sense, you are always getting some improvements. So when it comes down to a very simple thing, such as simulating e to the minus I ht for a time-independent Hamiltonian, then cubitization wins almost always. So that's the de facto standard. Although recently there has been some interesting work on Trotter-Suzuki method, which is still not competitive against cubitization, but in the future, it may actually be more advantageous. So I'll tell you a little bit about that. And this LCU, even though it's superseded for time by cubitization for time-independent Hamiltonian simulation, still for time-dependent Hamiltonian simulation, LCU is better because we currently do not know how to. So you can consider, you can use cubitization to do time independent Hamiltonian simulation, but at that point you're essentially doing the LCU. So I think it's fair to say that for time dependent simulation, the LCU method still win out. And each of these different approaches can be thought in the following way. So the cubitization, it's what is nice about them is that it's optimal, assuming that this block encoding unitary is given as a black box. So that means that you're not looking into this black box and trying to further optimize the structure. And it's actually practical. So this is the standard method of choice for quantum chemistry Hamiltonian simulation. And this is especially good. So that's why for many of these recent work that are discussing practical applications of quantum algorithms, cubitization is often what is being used. And also, if practically speaking, if you want to estimate the cost of these algorithms, cubitization is again very nice because as I told you last time, what it boils down to is ultimately the cost of the select and prepare operation. So, and then you just count the degree of the polynomial that you want to synthesize. So that's very easy. And for LCU, still for the time, so for time-dependent Hamiltonians, these things can be still advantageous. And you might think that this is a very strange application, but actually, you can actually do some smart things using these like time-dependent Hamiltonian simulation. So one interesting possibility was discussed by these folks, for instance. And here the basic idea is that you have a Hamiltonian, which can be broken down into two terms, let's say H1 plus H2, such that H1 is in some sense a very simple Hamiltonian. An example would be maybe a Hamiltonian like this. And H2 is a more complicated terms. Maybe things like and then what you do is that you basically go into the interaction picture. And once you go into the interaction picture, the Hamiltonian that you need to simulate is actually a time-dependent Hamiltonian, where you remove this simple Hamiltonian, but you instead address this complicated Hamiltonian by a simple Hamiltonian. So I share you'll remember the interaction picture from the undergrad quantum mechanics days. So this is the Hamiltonian that you want. And the nice thing about this is that if H1 is sufficiently simple, this is still some local Hamiltonian, right? Because, for instance, if you consider terms like this, conjugated by e to minus ith1, then this will be simply the it, let's see, zi plus zi plus 1 e to the minus it zi plus 1. And there can be cases for which the simulation of this interaction picture Hamiltonian is actually more advantageous. The basic intuition is that in Hamiltonian simulation, the larger the norm is, it is more difficult. The cost for the simulation increases. And the thing is, in the interaction picture, perhaps this unitary, these have unit norms. So if you're in a situation in which the conjugation by these e to the ith1, conjugation of h2 by this e to the ith1 is still a simple operator, and if, let's say, the norm of h2 is significantly smaller than the norm of h1, then you might be in luck. And then you may be able to actually simulate in a more efficient way compared to the naive time independent Hamiltonian simulation method. And again, the nice thing about the LCU is that they are like nearly optimal. They're not exactly optimal, but they're optimal up to polylogarithmic factor, some like log to the 2 or some factor like that. And log doesn't scale very fastly, so it's of course it would be good to make them even better, but it's not like a huge deal breaker at the moment. But the downside of the LCU methods is that when you actually look into the gate count estimate, it's somewhat more complicated, because what you end up doing is, even in the time independent Hamiltonian simulation, you're basically performing a Taylor expansion, and then so you need to keep track of these higher order powers of the Hamiltonian. And things become more complicated if you have time dependence, because then you'll need to use Dyson's equation. So you have multiple integrals, which you must do on your classical computer, and that's just a lot of information. I mean, all of these things can be done in polynomial time, but to actually work that out in detail is just a lot of work. So that's another downside of MCU. And now coming back to the very first method that we talked about, it was the Trotter-Suzuki method. And for a very long time, so this history, there's a very interesting history about the Trotter-Suzuki method. So for a very long time, this was like the simplest method that you could think of. And it was like the first method to show that in principle, there is an efficient quantum algorithm for Hamiltonian simulation. However, the rigorous bound that you could get from these early studies was not particular. What was actually worse than these more sophisticated methods such as LCU or qubitization. But when you actually do the simulation, people often found that you get a better result than what these naive bounds suggest. So that was known since, I think, like 2015-ish. And now this discrepancy between the rigorous bound and the empirical bound is almost resolved. So there's an interesting recent paper by Andrew Childs and his collaborators, in which they basically optimize this bound to death. And now the discrepancy is, at least for particular models, all the way down to, let's say, like factor of 5 or something. Whereas if you wind back 5 or 6 years ago, then this discrepancy was like multiple orders of magnitude. And good. And that's all good. But what is interesting about more recent versions of Trotter-Suzuki method is that they behave differently than the LCU or the cubitization methods. So yeah, so let me tell you more about that actually, because it's pretty interesting. So how do we calculate the cost of these algorithms? Like what we essentially do is that in Trotter, like we just use the Trotter-Suzuki decomposition and then just count the number of gates. In the cubitization, we estimate the cost by this select plus prepare subroutine. And I've already told you that in the prepare step, as well as the select step, if we have, let's say, n terms, so let's say we can decompose the Hamiltonian into this form. Then select and prepare using the simplest methods has a gate count of order n, in order n. And and the goal is, of course, to perform this e to minus IHT, and the number of time steps that you need to apply to for this select and prepare. So number of iterations of select and prepare roughly scales as this thing, which is not exactly the norm of the Hamiltonian, but it's something similar to that. And let's see, times t. Obviously, the longer time you need to simulate, the more costs you have. So that's for cubitization. This is the cost of the cubitization. So combining all these things together, the cost would be order n times alpha 1 t. And I'm assuming that the accuracy is constant. So like this will actually depend as like log 1 over epsilon, but I'll suppress that. So if you look at the randomized, and the keyword here is randomized, Trotter-Suzuki method, what you do is kind of funny. So what you do is that you first write down your Hamiltonian into this standard form. And depending on the weight of this alpha I, you apply individual Trotterized version of this individual local terms probabilistically. So you apply e to the I theta pi with probability. It depends on alpha I don't remember the precise form, but basically the larger the alpha i's, you have a higher probability of actually implementing this. And you do this for a fixed angle theta, okay? And if you do that for a sufficiently small theta, then you actually end up applying the time evolution. And then what you realize is that the cost here is actually order and there are some other constant that depends on more details about the Hamiltonian, but I just wanted to compare using the same n, this thing and that thing. So so the thing is, the important thing here is that this n factor here is removed in this randomized Trotter-Suzuki method. And that's the interesting bit about these like new generations of these Trotter-Suzuki methods. They fundamentally do not depend on the number of distinct terms in the Hamiltonian. So hypothetically, if you have a Hamiltonian that you want to simulate, and if you have an exponentially many such terms, then the cubitization will, well, take an exponentially long time, even to apply a single step of this select and prepare. But if you apply a randomized Trotter-Suzuki method, then the only thing that will matter will be actually the norm of this thing. So because of this, when this method first came out, people had hopes that maybe this line of approach can outperform cubitization. But it's important to realize that even though it might look like the randomized Trotter is better than cubitization, the dependence on error is different. On epsilon is log 1 over epsilon divided by log 1 over epsilon. Whereas here, dependence on epsilon is polylog. This is poly 1 over epsilon. So if you require higher precision, then this factor will be much, much worse than this factor. So in practice, it turns out that at least for quantum chemistry Hamiltonians, the cubitization method still wins. But it's an interesting open problem to understand if there is a cubitization version of this, in a sense that is there a version of cubitization that is insensitive to the number of distinct terms in the Hamiltonian? And this is not known.
So is it fair to say that the randomized Trotter-Suzuki is somehow a hybrid of the ideas from something like the Monte Carlo simulation and the conventional Trotter-Suzuki method?
Let's see. It is I mean, in some sense that is true, because you literally choose these PIs randomly. So yeah, there is a randomness in the output
that underlies which PI to choose with what weight.
Yeah, so this is that rule is written in this paper. So I don't remember the details now, but basically, roughly speaking, the larger the alpha I is in absolute value, you have a higher probability of applying this Pauli, which makes sense because yeah. Okay, good. All right, so that was just a summary of the state of affairs for the Hamiltonian simulation. Actually, I think it is worth mentioning. So nowadays, like, what do people work on Hamiltonian simulation? I guess there are like a couple of open problems. So, for instance, if you have like a time-dependent Hamiltonian, like I told you that LCU method is the best, but still somehow this method is very complicated. So it'd be nice to have a version of cubitization or a version of LCU, which is as nice and easy as cubitization. And also, I think it's still unclear if there's a regime in which this randomized Trotter method wins out over the other methods. And I think there is such a possibility, and maybe more study is needed in this direction. Okay, so I'll end the Hamiltonian simulation part with that. And now, now that we've learned so many of these tricks, I thought it would be good to at least spend like 30 minutes of our time explaining how what we've learned can be extended to more general situations. So I hope so we already discussed this funny example. So we discussed the utility of applying a weird time evolution, let's say generated by this weird operator. And this was actually useful because for the purpose of quantum phase estimation, it was much easier to implement this operation compared to, you know, this e to the IHT. So examples like this suggest that there's a room to study applications of these unphysical operators. And there's a very nice framework called quantum singular value transformation, which is a generalization of qubitization, which allows us to think about these possibilities in a very convenient and flexible way. And because this is not too different from qubitization, I just wanted to tell you about how these things work. So it's really simple. So let's remember last time we assumed the input model. So we assume that we have a block encoding of the unitary. So we have U of H, which has this block diagonal form, which is in this form where in the top left corner of the block, we have a n by n Hermitian matrix. And basically, this Hermitian matrix assumption is unnecessary. So we can consider a more general input model. So, and that's very simple. Well, you just change this H into A, okay, where A is just a general matrix, general n by n matrix. And of course, for a general matrix, you can perform what is known as the singular value decomposition. So that's a decomposition of A into this form where U and V are unitary matrices. And S is a diagonal matrix. Diagonal and non-negative matrix. And of course, if A is Hermitian, then U is equal to V. But more generally, they're not. And using a very similar idea that we discussed in qubitization, it turns out that you can actually synthesize basically a polynomial transformation of A. So when I say polynomial transformation of A, what I mean is that if you're given A equals U S V dagger, then I'm transforming that such that U and V remain the same, but the singular values are changed from S to P of S. So that's what I mean. And clearly here we're just changing the singular value. And so this algorithm is known as the quantum singular value transformation. And this is very powerful because well, first of all, it subsumes the qubitization framework, and it often leads to very simple and efficient quantum algorithms for a variety of problems. So we already discussed Hamiltonian simulation. This was covered by the qubitization framework. But you could maybe do things like this. So you begin with some state psi, and then you apply a inverse on psi to normalization. Okay, so this is one thing that you may want to do, and you can do that. I mean, a minus 1 is not a polynomial, obviously, but if it has a if none of its eigenvalues are 0, if it's like bounded away from the 0, then you can approximate 1 over x by some polynomial. And people know how to do this. So you can do that. And we've talked about amplitude amplification like a couple of lectures ago. There's a very natural way to implement that using quantum singular value transformation. And you can also do things like fractional query. So suppose you know how to implement the matrix, unitary matrix U, you can actually, instead of applying U square or U cube or U to the 4, you can apply U to the alpha, where alpha ranges from 0 to 1. And quantum singular value transformation allows you to do this in a nearly optimal way for a variety of these tasks. So when you develop these kinds of algorithms, again, you're left with often two questions. But that's good because it makes the problem much simpler. In a way, the problem is like more structured. So whatever quantum algorithm that you want to develop in this framework, what you need to ask is very simple. So first, you want to phrase your problem in such a way that for an arbitrary given input state, you want to apply some f of a times psi, applied to psi, where f is some function and a is some general matrix. Because quantum singular value transformation, it tells you how to do this, provided that f is not too crazy, and if you can encode a into a unitary. So of course, and while we don't know if your problem can be rephrased in this way, the fact that you have all sorts of these like well-known quantum algorithms reproduced by this framework suggests that this is a very broad and useful framework, and that is likely to be applicable to many different problems. So that's the upshot. But of course, the main question is, are these two? Well, first of all, how do you actually encode A into a unitary? So that's one question. And for Hamiltonian simulation, we discussed very explicitly how to do that. But obviously, in general, it's not at all clear how you can do this. And the second question is, how well can you approximate f of x by a low degree polynomial? Because remember, the cost of this cubitization was the degree of the polynomial. And the same applies to quantum singular value transformation. So if you can approximate the same function using a lower degree polynomial, then you're effectively reducing the cost of your quantum algorithm. And yeah, so maybe I'm being too simplistic here, and I probably am, but I think for all practical purposes, oftentimes the f of x that you want to approximate is not like a completely crazy function. It's usually some nice function like 1 over x, like log x or things like that. And oftentimes there's a very well-established approximation theory for approximating such functions using low degree polynomials. This is just a subject that has been studied for such a long time. So for all intents and purposes, I think it's fair to say that this problem is like most of the time already solved. It's very rare that you actually have to do the job on the second problem. But I think a more difficult problem is answering this question 1, because how do you actually encode A into a unitary? And this is really, you can only say this in a case-by-case basis. So usually people come up with new methods to do that, and people build upon these new methods to find an efficient encoding of A into a unitary. And fortunately, there are already very useful frameworks for block encoding. One was select plus prepare. I'm sure at this point we've heard about this a lot. The another example was the purification of the density matrix. So I've told you how this works. What this does is that the top left corner, you have some density matrix, sigma. And you can do this given if you can prepare a purification of sigma. And I told you how you can do that in the last lecture. And there's another input model which is the sparse matrix model. So this is the model in which imagine you have a humongous matrix, say n by n matrix, and the matrix is sparse. So let's represent the row, the column index as I and the row index as j. And then what you do is that given I, it'll output. I'm imagining that there is some magical function that given I outputs a set of j's such that let's call this as a. aij is non-zero, and moreover, given I and j such that aij is non-zero, there's a transformation such that you do this. So you can add like an element of aij. Okay, so it's less clear how you can do this efficiently in general, but once you assume that you have somehow constructed such a unitary, then you can use this to solve systems of linear equations. Okay, but you might wonder, I mean, these are all nice, but there's always this possibility that maybe none of these will actually work for your purpose. So if that's the case, then what do you do then? Maybe that's just the end of the story. But I wanted to tell you that there's actually a little bit more that you can do with, and the reason why this works is fairly trivial. So I just wanted to tell you about that. And this is the I don't think there's a standard name for this, but it's something that I like to call as the block encoding arithmetics. And what it says is the following. So the moral of the story is very simple. So suppose you have unitary encodings of these matrices. So you have U of A1, which is encoding A1 in this top left corner, U of A2, which encodes A2 on this top left corner, and you get the pattern. And then, so if you already have these unitary encodings of these matrices, then you can actually synthesize any unitary encoding. Let's see, maybe let's call this A tilde, where A tilde is a up to normalization. In the algebra, generated by these things. And what I mean by algebra is that you can multiply two matrices, you can sum over two matrices, and you can take their arbitrary linear combination over complex numbers, and you can do all of that. Okay, so that would be the moral of the story. And it's pretty simple to see why this works. So just to be clear, to prove this claim, what we need to do is very simple. So given unitary encodings of two matrices, we need to construct the unitary encoding of alpha A plus beta B, and also AB, because then we can generate the full algebra up to normalization. Good. So any questions so far? All right, then let me tell you how that works. So let's start with something easy, like a scalar multiplication. So obviously, if we begin with a unitary encoding of, let's say, A1, we cannot hope to multiply an arbitrarily large scalar, because then we will violate the unitarity. So by scalar multiplication, I just mean that some operation that decreases the norm. So how does that work? So let's say we have this access to the unitary encoding. this, which acts in a standard way. So this G psi, it has this property that if you apply G A tensor identity S and calculate the overlap with this thing, then it's 0. Okay. And what you just need to do is the following. So you just introduce one extra qubit. Let's call it as Q. And this lower part is A and S combined together. And you just apply a controlled unitary. Okay. So if Q is in the 0 state, you do nothing. If Q is in the 1 state, then you apply unitary of A1. And if you apply this unitary to a initial state, let's call it as control unitary. To say an arbitrary state alpha 0 plus beta 1 on this qubit Q, and this state, then you just simply get that plus beta 1Q So you can see that we were able to rescale A1 into beta A1, wherein the new ancilla state is simply declared to be 1Q GA state. Okay. So so I'm not discussing some of the details. So in principle, you have to make sure that the initial state is also 1Q GA, and then you'll have to change this first extra qubit state into alpha 0 plus beta 1, but that's just extra detail. So so technically speaking, this new version of unitary encoding, you must also add this single qubit unitary. But in any case, you can see that you can do scalar multiplication as long as it doesn't increase the norm. So that's very easy. And the addition, in fact, more generally, a linear combination is also very straightforward. The circuit is very similar, but with some minor differences. And they're similar in the sense that you still, again, introduce one extra qubit. The difference is that, let's see. So now I'm going to introduce two ancillas because what I want to do is that I want to have access to unitary encoding of A1 and A2, and they will generally require a different type of ancillary state. So let's see. If you apply this to that state, then this would be GA1, A1 psi S plus G psi, let's call this 1 perpendicular. And if you apply this to GA2, then GA2, A2 psi S plus G psi comma 2 perpendicular. So what you would do is basically first you apply, let's see, so this thing will be control unitary A1, yes, and you would like to apply the control unitary A2, except you want to apply a Pauli X operator in between the two. Okay, so if you begin with an arbitrary quantum state, let's say alpha 0 plus beta 1 on the Q state, then what you can see is that, let's see. So it's a simple algebra. So let's just go through this. So after we apply this unitary, what you get is, let's see. So if it's in the 0 state, let's see. So if Q is 0, in this first step, you don't do anything, because if it's 0, then you don't do anything. And then you flip your state to 1, and then you apply this control unitary A2. So in that case, you get alpha 1Q, GA1, GA2, A2, psi S. And if you begin with the 1 state here, then you first apply the control unitary A1, and then you apply X, so the Q state is changed from 1 to 0. So this thing is not applied. And therefore, we get okay. So what you end up getting, plus some junk. Yeah. So alpha 1Q. So we get alpha A2 plus so again, up to a single qubit unitary transformation, you can implement a linear combination of A1 and A2 as a unitary oracle, just by changing your definition of the ancillary state to, let's say, GA1, GA2, tensor, say alpha prime 0 plus beta prime 1, depending on which linear combination that you want to implement. So that's very easy. And multiplication is actually easier, because all you need to do is that you apply this unitary encoding in sequence. So let's say we have U of A1 and U of A2. What you just need to do is that you begin with this state, 2 psi of S, and you apply U of A1 and you apply U of A2. And this ends up being A2, A1 applied to psi s plus, let's say, G psi this thing, where this state is, if you apply the bra of this thing to G psi perpendicular, then this is equal to 0. So this way we can see that given access to the unitary encoding of, let's say, A1, A2, all the way to AN, you can construct basically anything. You can consider its linear combination and products and basically anything that you want. So are there any questions so far?
So is it somehow by accident that this algebra is realized by the unitary what is it, forgot the term, blocking or
Blocking
something?
coding?
Blocking coding, or is there some sort of mathematical reason why this should work?
Let's
Like
see.
with
So
this algebra preserving mapping, maybe?
I'm not sure. So I mean, yeah, I don't know. I mean, all I can say is that given given access to two unitary encodings, we can construct their linear combination because of this discussion in the previous slide, and also the multiplication because we just did that. So and those two are the operations that generate the full algebra. So I think that just completes the story. I don't know if there's a deeper reason actually.
But anyway, it works.
Yeah, it works. Yes. Yeah.
Okay.
Yeah. Right. Yeah. So one, slight tangent, but like one interesting thing that you can, as a slightly non-trivial application, one thing that you may want to do is the following. So let's say I have a unitary encoding of H, sorry, let's say I want to consider a Hamiltonian, which is some original Hamiltonian plus some perturbation. Then, actually, that's not the greatest choice. Let's say, okay. And suppose I have access to unitary encoding of H1 and unitary encoding of H2, then you can actually use this construction that I showed in the previous slide slightly so that you can construct a unitary encoding, which is simply of this form. Where you simply apply a single qubit rotation here. Where theta and theta prime are determined by S. So by just tuning these angles, you can actually construct a continuous family of Hamiltonian that interpolates between the two. So it's a very flexible framework. Yeah, so the moral of the story is that basically this quantum singular value transformation framework, the key thing is how to construct this unitary encoding. And there are flexible ways of doing that. So at the high level, there are these like nice models on how to do that. So like prepare, purification density matrix, and sparse matrix. But you can actually even find, even construct very weird combinations of them. Because for instance, you can maybe have a unitary encoding of matrix A1, which is like a local Hamiltonian in a many-body system. And let's say A2, which is a purification of density matrix. And you can somehow synthesize very weird operators, like 1/2 A1 plus A2. So this would be local, and this would be non-local. And somehow you can do like Hamiltonian simulation with these weird operators. You can do polynomial transformation. So there are all sorts of things that you can do. And I don't know any like application of like mixing these like a different input models, but maybe there is something to be done there. So it's just one food for thought. So yeah, so that's what I wanted to say for the first half. So take some questions and have some rest.
This so-called purification of density matrix, I must confess I don't really know much about this purification, but whatever that may be, is there a possibility that this purified operator A2 reflects some sort of a physical system, some sort of a physical Hamiltonian?
Let's see, the purified system. So it could be anything really.
But it's a Hermitian operator.
It'll be a Hermitian operator because it's a density matrix. But so generally this will not be a local operator. So I guess the answer really depends on what kind of density matrix that you're preparing. Maybe you can consider one physical example that you may consider is the following. So let's say you have a spin chain, like a one-dimensional quantum system, and then you begin with some product state, let's say all spin-up state, still a pure state, and then you evolve this entire thing by some Hamiltonian. Let's say you do some like little trotter thing. So it's still a pure state, and then you trace out this red region. Okay. And you're left with these like the 3 spins or something. Then probably if the system thermalizes well, then probably the reduced density matrix will be of this form, E2 minus beta H. It's called as A for some temperature beta, like up to some approximation. So in that case, the unitary will be E2 minus beta HA of this form. So for instance, if you do like Hamiltonian simulation with this thing, you're going to end up implementing things like this. Yeah.
I see. Okay.
Yeah.
Looks interesting.
Yeah. Any other questions?
I have a naive question. What are the sort of unsolved problem in these approaches?
In which direction?
Like let's say I want to do some quantum simulation using this like LCU or cubitization or whatever method. Like which topics that people are interested in, sort of?
Let's see. I think these like high level algorithms are mostly done. Let's see. I think some people wonder about like whether you can, in cubitization, you get like a cost of like order t plus log whatever epsilon. But this only applies to time independent Hamiltonian.
Mm.
And I guess some people wonder, can we do it for time dependent Hamiltonian?
Mm.
But this seems like a very difficult problem. I think this is like the one of the few high level open problems that are left. Usually, let's see. So lately, it has been mostly about optimizing the select plus p pair. For quantum chemistry Hamiltonians. So I guess that's still an ongoing work. I should confess that while generally speaking, if the Hamiltonian has nice symmetries, you can often do better. I'm not aware of any like nice general framework which relates the cost of the quantum algorithm to the symmetries of the Hamiltonian. So maybe there's some like a nice general work to be done there. Yeah, these are just my thoughts.
Thanks.
Okay.